75 million light-years from here. A star once registered at 100 times the mass of our Sun. It radiated 2.5 million times brighter, and then it stopped existing. Not dimmer, not drifted behind some passing object, gone the way a drawer feels empty after you check it a fifth time, your hand closing on nothing. Right now, if you aimed every telescope we own at that patch of sky, you would see only the ashes of an event no one recorded. No flash, no alarm across an observatory network, no astronomer waking up because something detonated. Somewhere between 2011 and 2016, inside a small, faint galaxy, one of the most massive stars ever catalogued simply vanished from the data. Massive stars are supposed to die loud. They are supposed to light up their host galaxy for weeks, sometimes outshining every other star in it combined. That is the contract. That is the rule every textbook prints. This star broke the contract. So here is what we are left with. Either that star still lives, wrapped in something dense enough to swallow the light of an object 2.5 million times brighter than our Sun, or it collapsed straight into a black hole without producing the explosion physics demands. Two explanations, both strange, neither confirmed. Prepare yourselves. We begin. This is not a lecture. Think of it as a case file, the kind a detective keeps on a desk with photographs clipped to it and question marks scrawled in the margins. The tension at the center is simple to state and hard to sit with. Astronomers have a rulebook for how stars this massive end fuse elements, build a core, collapse, explode, leave a remnant behind. This star held every property that rulebook expected to see, and then it exited without following a single step. Two suspects stand at the center of the investigation. One, dust. The idea that the star is still alive, buried under material thick enough to block its signal. Two, a failed supernova. A star that skipped the explosion and folded straight into a black hole. And here is the part worth sitting with before we go further. This case does not get solved by the end of this video. It has not been solved in the newest data astronomers have published. That is not a screenwriting choice. That is the actual current state of the science. Before the star went dark, nobody was watching PHL 293b. This dwarf galaxy, small and faint, was catalogued decades ago and mostly ignored since. Astronomers call it the Kinman dwarf, and if you asked a room full of professional stargazers to name it before 2019, most would draw a blank. It is not spectacular to look at and not close, the kind of object that ends up as a footnote in a survey rather than the subject of one. Except dwarf galaxies like this one hold something useful buried in their chemistry. They are low in metal content, short on the heavier elements that build up over generations of stars living and dying and seeding the gas around them with fusion byproducts. That scarcity mirrors conditions from billions of years ago, back when the universe itself was young and had not yet enriched its gas clouds with heavy elements. Study a metal-poor dwarf galaxy today, and you're getting a stand-in for the kind of environment that built some of the very first generations of stars. Which is why a massive star turning up inside one of these galaxies matters. A chance to watch extreme stellar behavior unfold in conditions resembling the deep past, without needing a time machine. But here is the catch. The Kinman dwarf sits 75 million light-years away. That is far enough that no telescope built by human hands, not Hubble, not the biggest ground-based instrument on Earth, can resolve a single star inside that galaxy as its own separate point of light. Every star in PHL 293b blurs together into one smeared patch on our instruments. So how do you study a star you cannot actually see?
You study its fingerprint.
Astronomers use integrated spectroscopy, and the idea behind it is simpler than the name suggests. Instead of looking at the star directly, they take the combined light of the entire galaxy and break it apart, wavelength by wavelength, the way a prism splits white light into color. Buried in that spread of color are narrow spikes and dips, specific patterns tied to specific physical processes happening in specific kinds of stars. A star behaving in a particular violent, unstable way leaves a signature in that spectrum, distinct enough to identify even though the star itself is invisible. This is the only way anyone has ever studied this object. Not a photograph, not a close-up, a signature mixed into the total light of an entire galaxy and pulled back out through careful analysis. Which means everything we know about this star, its mass, its brightness, its behavior, comes from indirect evidence. Nobody has ever seen it. Nobody ever will. Not with the tools currently available. Every claim made about this star is an inference, built from light that traveled 75 million years and arrived already blended with the light of millions of other stars around it. And that is exactly why its disappearance is such a hard case to crack. When a signature vanishes from a spectrum, you do not automatically know whether the source went quiet or got hidden or simply changed into something the old detection method cannot catch. No photograph to check for a shape no longer there, only a pattern that used to show up and now does not. The signature pulled out of that spectrum belongs to a specific kind of star. The name sounds clinical until you understand what it describes. A luminous blue variable is a massive star tearing through the most violent, unstable stretch of its life, the phase right before something has to give. Picture the biggest, hottest stars a galaxy can produce. Most of their lives, they burn steady, fusing hydrogen into helium in a long, controlled process. But once a star gets massive enough, somewhere north of dozens of times the mass of our Sun, it hits a stage where steady is not an option. Gravity crushes inward with tremendous force, and the fusion happening in the core pushes back just as hard, and the balance between those two forces gets shaky. The star starts throwing off huge amounts of its own material just to survive the internal pressure. That shedding, that violent instability, is what an LBV phase actually is. We do not have to guess what one looks like because our own galaxy has one. A star called Eta Carinae sitting inside the Milky Way, close enough that astronomers have studied it in detail for close to 2 centuries. In the 1840s, Eta Carinae threw off so much material in a single event that it briefly became one of the brightest objects in the entire night sky, rivaling Sirius, before fading back down as the ejected material cooled. That is the behavior we are talking about. Not a slow, gentle dimming, a star ripping chunks of itself away and flinging them into space. Sit inside that decade for a moment, because the record is more detailed than you would expect for something that happened before photography existed as a science. Observers in the southern hemisphere tracked Eta Carinae night after night through the 1840s, watching it climb in brightness, dip, climb again, in what became known as the Great Eruption. By 1843, it had brightened enough to become the second brightest star in the entire sky, outshined only by Sirius itself. And Sirius is less than 9 light-years from Earth. Eta Carinae was doing that from roughly 7,500 light-years out. Do the math on what kind of output that requires, and the number gets absurd fast. For a star to look nearly as bright as our nearest stellar neighbor, while sitting almost 1,000 times farther away, it has to be pumping out light on a scale that barely fits inside normal stellar physics at all. And it did not do that quietly. Astronomers now estimate the Great Eruption threw off something like 10 to 20 times the mass of our Sun blasted outward over roughly 2 decades of eruption, not in one clean instant, but in a sustained, violent shedding that kept going and going. That material did not just vanish into open space either. It piled up around the star in 2 lobes, one on each side, pushed outward, until it formed a structure with actual shape, actual visible geometry, when telescopes eventually got good enough to resolve it. Astronomers named that structure the Homunculus Nebula because through early telescopes, its twin-lobed shape looked something like a tiny human figure with 2 shoulders. It is still there today, still expanding, still glowing from the leftover heat of an explosion that happened before the American Civil War. Here is what makes the homunculus useful for this whole investigation, rather than just a historical curiosity. It is a fossil record. You can look at that nebula today, measure how fast it is expanding, and work backward to figure out exactly how much energy and material went into building it 180 years ago. It is proof, sitting in the sky right now, that a star can throw off a colossal fraction of itself, survive the process, and keep burning afterward. Eta Carinae did not die in the 1840s. It is still there, still one of the most studied stars in the galaxy, sitting inside the wreckage of its own outburst. There is also a complication in Eta Carinae's story that matters for how astronomers think about LBVs in general. It is not a single star. It is a binary, two massive stars locked in a tight, eccentric orbit around each other. One of them a genuine LBV and the other a smaller but still massive companion. That second star sweeps close enough, every 5.5 years or so, to interact with the primary's extreme wind, and some astronomers think that close pass may have helped trigger or shape the great eruption itself. The debate over how much the companion star matters, whether it merely perturbs an already unstable primary or actively drives the instability, is still not settled. That question matters here because it raises something worth remembering for every LBV case, including the one in the Kinman dwarf. Sometimes what looks like one star behaving strangely is actually two stars locked together, and untangling which object is doing what gets harder the farther away you look. Eta Carinae is not the only known LBV, and it helps to see it standing next to its relatives rather than treated as some singular oddity. Ag Carinae, another well-studied example in our own galaxy, shows the same pattern of dramatic brightness swings paired with an expanding shell of ejected material, evidence of its own past outbursts written into the nebula surrounding it. P Cygni, visible to the naked eye, and recorded by observers as far back as the late 1500s, brightened suddenly, faded, brightened again over centuries, cycling through outbursts long before anyone had a name for what was happening. Doradus, out in the large Magellanic Cloud, gave an entire subclass of these stars its working name. Astronomers still sometimes call LBV brightness swings S Doradus variations, because that star's behavior became the reference case for the whole category. Line all of these up together, and a pattern holds steady across every one of them. Extreme mass, extreme instability, and a documented history of throwing off material in fits and starts rather than a slow, steady wind. So what actually drives an outburst like this? The answer sits in the physics of how radiation itself can shove matter around. Every star holds itself up through a balance between gravity pulling in and pressure pushing out. And for most of a star's life, the outward push comes mostly from ordinary thermal pressure, heat generated by fusion. But in a star this massive and this luminous radiation pressure, the physical push of photons themselves slamming into the outer layers, starts doing serious work too. Push a star's luminosity high enough, and radiation pressure alone can start shoving the outer envelope outward against gravity's pull, cross a critical threshold, one astronomers call the Eddington limit, and radiation pressure exceeds what gravity can hold down. The outer layers do not just get nudged, they get launched. There is a wrinkle in the star's own chemistry that makes this worse at exactly the wrong moment. Deep in the outer layers of a hot, massive star, there is a region where iron atoms, stripped of some of their electrons, become extremely good at absorbing radiation, far better than the layers just above or below. Astronomers call this the iron opacity bump. Where that bump sits, radiation pressure spikes locally, sometimes pushing the local luminosity past the Eddington limit, even if the star's overall average luminosity sits below it. That is not a minor detail. It means an LBV does not need to be uniformly over its limit everywhere at once. It just needs one layer, one shell inside its structure to hit that threshold, and that layer becomes unstable enough to drive an eruption on its own, flinging material outward in what astronomers call a continuum-driven wind. A wind pushed not by absorption lines the way ordinary stellar winds work, but by the sheer bulk of continuous radiation pressure shoving against nearly everything in its path. That is the mechanism behind the outbursts. Not a single dramatic failure, but a star running so close to its own structural limit that entire layers periodically give way and get thrown outward. Then the star settles, rebuilds some equilibrium, and does it again years or decades later. It is why LBVs look unpredictable rather than steadily variable. The instability is not a slow leak. It is closer to a pressure valve that blows intermittently whenever conditions inside line up in exactly the wrong way. Astronomers do not classify a star as an LBV casually either. There are specific markers they look for, and they tend to show up together rather than in isolation. Broad emission lines from hydrogen, layered over narrower features from surrounding nebula gas, are the first flag, because they mean there is a dense stellar wind actively feeding a glowing shell around the star. A documented history of brightness variation, ideally tracked across multiple years or decades, is the second, because a single bright moment could be almost anything, but a repeated pattern of swings is much harder to explain any other way. and a spectrum that shifts character between quiescent and eruptive states, sometimes looking hotter and bluer, sometimes cooler and more swollen, rounds out the profile. Put those three markers together consistently over enough time, and astronomers are confident enough to hang the LBV label on a star even when they cannot see it directly, which is exactly the situation with the star in PHL 293b. The instability shows up in the numbers. LBVs drive winds fast enough to strip serious mass off the star every single year, and on top of that steady wind they go through outbursts. Sudden and dramatic surges where the brightness can swing by a factor of several times in a few years. That is not typical stellar behavior. Most stars hold roughly the same brightness for millions or billions of years running, but an LBV can look like an entirely different star in successive decades. Brightening, dimming, brightening again, driven by whatever is happening in its unstable interior. So, how do you spot one of these from 75 million light years away, buried inside a spectrum made of blended starlight? You look for the fingerprint that all that ejected material leaves behind. As the star throws off gas, that gas does not just disappear. It sits around the star in a loose, glowing shell, heated and lit up by the star's own radiation, and it emits light at very specific wavelengths. In a spectrum that shows up as broad, strong emission lines, especially from hydrogen, sitting on top of narrower features from the surrounding nebula. The star itself might be too far to make out directly, but the gas around it lights up in a way that is unmistakable if you know where to look. And this phase is not just a curiosity, it is a warning sign. When a star enters LBV behavior, the clock has started counting down towards something dramatic. Nature does not sustain that level of instability indefinitely. LBVs are a late chapter, not an early one, and every astronomer who spots that signature knows they are looking at a star running out of stable ways to hold itself together. There is a reason this phase matters so much for everything this investigation is chasing, and it goes beyond the drama of the outbursts themselves. Every bit of mass an LBV throws off during these eruptions is mass that will not be part of the star when its core finally gives out. That matters enormously for what happens next, because the mass sitting in a star's envelope at the moment of collapse helps decide whether the explosion succeeds or fails. A star that sheds huge amounts of its outer layers during its LBV phase arrives at core collapse, lighter, less tightly bound, easier in principle for a shockwave to blow apart. A star that holds onto more of its bulk, the way a metal-poor star tends to, arrives at collapse heavier, denser, and harder to explode. The LBV phase is not a side plot. It is the mechanism actively reshaping how much material this star will be carrying into the single most important moment of its life, the moment we are about to spend the rest of this investigation picking apart. Which is exactly the signature that showed up, again and again, in the spectrum of PHL 293b. Consider the numbers on what lived inside that galaxy. The star was roughly 100 times the mass of our Sun. Not 100% more massive, 100 times over. And in brightness, astronomers estimate it at roughly 5 million times the Sun's luminosity. Sit with that second number for a moment, because it is easy to read past. 2.5 million. If you lined up 2.5 million suns, side by side, all burning at once, you would be looking at roughly the light output this single star produced on its own. One object doing the work of an entire small cluster of stars. That is not a metaphor. That is the measured output of a single star, a point of light so intense it defies the scale we use for everything else in the sky. It is a fact, measured and confirmed. To grasp the scale of that gap, consider this. Our sun's light takes 8 minutes to reach us, and it is already the dominant source of light and heat for an entire solar system. Now, imagine something so much brighter that it does not just light up its own neighborhood, it lights up its whole galaxy. That is not a candle in a dark room. That is a fire so large you would see its glow from 3 counties over, a distant orange smear on the horizon, before you ever saw the flames themselves. That is the kind of light we are talking about. And that is not an exaggeration built for effect. Astronomers who studied PHL 293b have stated plainly that this star's light was strong enough on its own to noticeably brighten the entire galaxy around it. The Kinman dwarf is small after all. It is not a sprawling spiral with hundreds of billions of stars diluting any one source. It is a modest, low-population galaxy and this one star was pumping out enough light to shift the measured brightness of the whole system. One object, meaningfully changing how bright an entire galaxy appeared from 75 million light-years away. Put the mass and the brightness together, and you get a star that ranks among the most extreme ever discovered in a metal-poor environment. Recall what we covered about the Kinman dwarf's chemistry. Thin on heavy elements, closer to the conditions of the early universe. Stars born in that kind of environment tend to hold on to more of their mass over their lifetimes, because the winds that normally strip material away depend on those heavier elements to work efficiently. Less metal content generally means a star keeps more of what it started with. And this star started with a lot. 100 solar masses, retained long enough to reach this violent, unstable LBV stage, while still carrying most of its original bulk. This star was not just any LBV. It was an LBV in a metal-poor galaxy, which means it had held on to its mass longer than most. The combination of extreme mass, extreme brightness, and extreme instability made it a prime candidate for a spectacular end. Every model predicted it. Every observation supported it. And then the star simply stopped being there. But here is where the paradox sets in. And it is the paradox this entire investigation is built around. A star this massive, burning this bright, sitting this deep into an unstable phase that is supposed to be a countdown towards something explosive, should not be able to leave quietly. Every rule in the stellar playbook says a star of this. Between 2011 and 2016, the galaxy called PHL 293b sat unmonitored. No telescope tracked it. No instrument recorded its light, the entire window when its star could have changed, and nobody saw a thing. That is not negligence. That is how the game works. Telescopes are booked years ahead, fought over by astronomers with competing targets. A dwarf galaxy that had already delivered 10 years of quiet. Expected data does not earn a permanent slot. Resources go where the action is. And PHL 293b, by every available measure, was not action. So the instruments looked elsewhere. Other galaxies, other stars, other questions that seemed more urgent in the moment. Which means whatever happened to this star happened in the dark. Not literally dark. The light was still crossing space, still arriving every night, but nobody collected it in a way that would let us reconstruct the story later. And here is where the silence gets uncomfortable. If that star had died the way a star of its size is supposed to die, the wide field surveys scanning the sky during those years should have caught it anyway. A supernova from a star 100 times the mass of the Sun does not stay quiet. It announces itself. Automated pipelines are built to flag a new point of light appearing, where a faint galaxy used to sit. That is not a subtle signal. So the archives were checked. Every survey with any coverage of that patch of sky, cross-referenced, searched, combed through for any hint of a new bright source. Nothing. No transient. No flagged event. No archived image showing a brief spike in brightness that anyone circled back to identify. The record is clean. Clean in exactly the wrong way. But something did happen. The star that had shown up reliably for a decade was not there when anyone came back to check. Somewhere between 2011 and 2016 it left. And however it left, it did so without leaving the one piece of evidence every model says it should have left behind. High in the Atacama Desert, where the air is thin and dry, and exactly the kind of still that makes ground-based astronomy possible. The Very Large Telescope sits there, 4 separate instruments working together under the European Southern Observatory's banner. And this is where a team of astronomers turned their equipment back toward the Kinman dwarf. There was nothing dramatic about the decision to look again. No alarm, no suspicion. This was routine, the kind of follow-up that happens all the time. Check in on a known object. Keep the record current. PHL 293b had a well-established reputation by then. A small galaxy hosting one of the most extreme stars ever catalogued in a metal-poor environment. Routine follow-up on a known LBV means exactly what it sounds like.
You point the telescope.
You take a fresh spectrum. You expect to see what you have always seen. A decade of consistent data had built that expectation into something close to certainty. There was no reason walking into this observation to think anything had changed. They took the spectrum. They broke the galaxy's light apart. wavelength by wavelength, the same method used in every observation before this one. The signature was not there, not fainter, not shifted, not buried under noise.
Gone.
When the team looked at the exact wavelengths where the LBV's broad emission lines had shown up reliably for 10 straight years, there was nothing there to see. The pattern that had defined this object, the pattern that had made it worth returning to, had disappeared from the data entirely. If this were a single instrument on a single night, you would have every reason to pump the brakes. Equipment fails. Detectors drift. A single spectrograph having an off night is the first suspect any careful scientist checks before believing something extraordinary. So the team did not rely on just one. The VLT carries multiple spectrographs, separate instruments, built differently, calibrated independently. They used more than one on this galaxy. Every instrument came back with the same answer. No LBV signature anywhere in the spectrum, agreed upon independently by separate pieces of hardware that had no reason to fail in exactly the same way at exactly the same time. That is what rules out instrument error this early. A single broken detector explains a single bad reading. It does not explain 2 or 3 independent instruments, built by different teams for different purposes, all landing on the identical absence. If something were wrong with the equipment, you would expect inconsistency between instruments, not agreement. Instead, every tool they pointed at that galaxy told them the same thing. The star's fingerprint had stopped showing up. One clean night of data like this is enough to make any careful astronomer suspicious of the result itself, no matter how many instruments agree. A fluke is not always instrumental. Sometimes it is timing, coincidence, some unrelated fluctuation in the galaxy's light that happened to mask the signature on this particular pass. So they did not stop at one look. December 2019 brought the team back for a second look, months after that first null result. This is standard procedure whenever a result looks this strange. You do not publish on the back of one observation, no matter how many instruments agreed with each other the first time around. There is still a version of events where something about the galaxy's light, some short-term fluctuation, some quirk of timing, happened to mask the signature on that specific pass, without meaning the star was gone for good. The only way to close that door is to wait, then look again, on a different night, months removed from the first attempt. So they aimed the VLT back at PHL 293b and captured another spectrum. Same result. The signature was still missing, not faint, not partially recovered, but absent exactly as it had been months earlier, in the same wavelengths where a decade of prior data had shown it standing out clearly every single time anyone checked. That is the moment this stops being a fluke and starts being a fact. 2 independent observations, months apart, on different nights, with different atmospheric conditions, and the same absence. The probability that this is a coincidence is vanishingly small. And here is where it gets uncomfortable. Consider what 2 independent observations separated by months sitting on top of multiple independent instruments from the first round actually create. Not just confidence that the equipment worked correctly, but confidence that whatever changed about this star changed and stayed changed. This is the difference between a temporary anomaly and a permanent transformation. A short-term dip in brightness, some temporary quirk of the star's own variability, would have shown at least some sign of shifting between 2 observations spaced that far apart. Instead, nothing moved. The star's signature did not flicker, did not dim, did not return. It simply remained absent, as if it had never been there at all. The absence in December looked exactly like the absence months before it. So the timeline narrows. The window of disappearance now sits between 2011 and 2016, a 5-year gap in which something catastrophic must have occurred. Astronomers held solid data through 2011 showing the LBV signature present and consistent. They had 2 separate, independently confirmed observations in 2019 showing it gone. Whatever happened to this star occurred sometime in that gap, and it has not reappeared since. Not a blip, not a pause in an ongoing cycle. A vanishing, held steady for years, confirmed twice, by more than one instrument, on more than one night. This is not a star that faded. This is a star that stopped existing in the wavelengths where it had always been visible. At this point, the team was not sitting on a rumor or a preliminary hunch. They were sitting on a result solid enough to put their names behind. Mid-202, the European Southern Observatory made it public. The findings went into a paper in a major astronomy journal, the kind of publication that puts a result in front of the entire professional community, inviting scrutiny from anyone who wants to check the work. And that is the actual process here. Not a press release built on a hunch, but a peer-reviewed study built on years of archival data, plus 2 independently confirmed nights of new observations laid out for other astronomers to examine. The paper invited scrutiny, and scrutiny came. Other teams began checking their own archives, looking for similar disappearances, wondering if this was an isolated event or the first of many. And when ESO summarized what the paper found for the public, they did not dress it up. Their own language described the discovery plainly: the absence of an unstable massive star in a dwarf galaxy, where one had clearly been present before. Read that sentence again, because it is doing something unusual for an institutional announcement. It is not claiming a discovery of something new, but confirming the disappearance of something that used to be there. Astronomy is usually in the business of finding things. This is a paper about not finding something that should still exist. That inversion of the usual scientific narrative is what makes this result so unsettling. It is one thing to discover a new object. It is another to confirm that something we thought was permanent has vanished. But here is where it gets uncomfortable. Listen to the tone of that announcement, and you will notice it is careful in a way that stands out, with no confident declaration of what actually happened to the star. No single explanation presented as the answer. The language stays hedged, weighing possibilities rather than picking one and defending it. That hedging is not weakness, it is intellectual honesty in the face of incomplete data. That hedging is worth sitting with, because it would be easy to read it as scientists being cagey, holding back a conclusion they are not ready to share yet. That is not what is happening here. This is a case where the actual evidence splits cleanly into 2 directions, and neither direction has enough support to knock the other one out. The data show the signature disappearing. The data do not show which of the 2 remaining explanations produced that disappearance. When professional astronomers publish something without picking a side, it is usually because picking a side is not something the evidence allows yet, not because they are avoiding an answer they already know. So the paper laid out 2 possibilities side by side and left them standing. And that is where the mystery remains, unresolved, waiting for the next observation, the next piece of evidence, the next night when someone points a telescope at that patch of sky and sees what is there now. Start with the possibility that nothing actually died here at all. Under this scenario, the star never collapsed. It never detonated. It never left the universe in any final sense. It is still burning right now, tonight, somewhere in that galaxy. It just stopped being visible to us, not destroyed, hidden. Here is how that could work. Remember the outburst detected in the years leading up to 2011? That period where data showed the star aggressively shedding mass. An event like that does not throw off a light dusting of material. It drives out enormous quantities of gas, and as that gas drifts outward from the star, it cools, and cooling gas is exactly the condition dust needs to condense out of. Given the right density, the right chemistry, the right amount of time, an outburst like that could seed a genuinely thick cloud of dust in the space immediately surrounding the star. Picture what that means physically. The star keeps burning inside, business as usual at its core, while the material it threw off during that outburst settles into a shell around it, like a blanket pulled up and over its own light. Not a thin haze that lets most of the glow through. A blanket dense enough to catch starlight before it escapes, absorb it and hold onto it, rather than letting it travel outward toward any telescope waiting 75 million light-years away. The star does not need to change what it is doing. It just needs enough material sitting between itself and us. There is a second piece to this theory that does not require any dust at all. LBVs are documented to shift into an entirely different phase after a violent outburst, cooling down and dimming considerably as part of their normal behavior. This is not a hypothetical stretch invented to rescue this one case. It is an observed pattern in stars of this type. An LBV can go through a dramatic eruption and come out the other side measurably fainter and cooler than it was going in, sometimes for extended stretches, without that transition meaning the star has died. If this star followed that same pattern, Its spectral signature could have simply stopped standing out against the rest of the galaxy's light, not because the star vanished, but because it quieted down into something far less detectable.
We do not have to imagine what this looks like.
Our own galaxy already showed us. Eta Carinae's great eruption in the 1840s threw off enough material to briefly make it one of the brightest points in the entire sky, and it has spent the time since surrounded by an expanding shell of its own ejected gas and dust, dimmer than it once was, yet still very much alive. A massive brightness swing, driven by a massive outburst, with the star very much intact on the other side of it. That is not speculation. That is recorded history from a star we have been watching for generations. This is exactly what makes this theory appealing to a lot of astronomers weighing this case. It does not ask you to invent anything new. No exotic physics, no untested mechanism, nothing that requires rewriting a chapter of stellar evolution. Just an extreme version of something stars like this are already known to do. Sometimes the simplest explanation is the one that asks the least of the evidence. But hold that appeal at arm's length for a moment, because the survivor theory has a problem sitting right at its center, and it is not a small one. Dust dims a star. Dust does not erase a star's fingerprint. Those are two different things, and this case requires the second one, not the first. If you pile enough obscuring material in front of a bright source, what you get is a fainter version of the same signature, reddened and muted, weaker than before but still traceable if you know where to look. What astronomers found in 2019 was not a weaker signature. It was no signature at all. Every wavelength where the LBV's broad emission lines used to sit was clean, empty, showing nothing where something used to be unmistakable. That is a harder thing for a dust cloud to do than people assume walking into this theory. Here is why that distinction matters so much for a star like this one specifically. The signature astronomers were tracking was not just starlight. It was the glow of hot gas, sitting in a wind blown off the star itself, lit up by radiation coming from underneath. That kind of feature tends to survive even when a star's direct light gets buried. The wind exists outside the densest part of any obscuring shell, closer to the observer than whatever is doing the blocking. Wrap a star in a blanket of its own dust, and you would expect the wind signature to still poke through in some form, maybe distorted, maybe reddened, but present. A total blackout of every trace, wind included, is a much bigger ask than simply dimming a star's continuum light. And then there is the scale problem, which might be the harder one to get past. This was not an average star getting quietly muffled. This was an object bright enough to noticeably shift the measured brightness of its entire host galaxy, on its own, from 75 million light-years away. To hide something with that kind of output, the surrounding dust cloud cannot just be thick. It has to be extraordinarily dense enough to swallow output on the order of millions of suns and keep every trace of it from reaching us. That is not the kind of shell a single outburst typically produces, even a violent one. It is a much bigger structure than most LBV eruptions are known to build. Where does that leave the theory? Still standing, but on thinner ground than it looked like a few minutes ago. It is not dead. It is not disproven. It still works in principle, and it still asks for nothing beyond physics. We have already watched stars perform, but it asks for an unusually extreme version of that physics. Extreme in density, extreme in completeness, extreme in a way that pushes past anything documented so far in a star like Eta Carinae. A theory that requires the most extraordinary version of an ordinary process is still alive. It just rests on a foundation that is starting to show cracks. Which brings the investigation to the other suspect. The one that does not ask for an extreme version of anything familiar. The one that asks you to accept that the star simply is not there anymore, in any form, anywhere. Consider the second possibility. It does not ask you to imagine a hiding place. It asks you to accept something stranger, that the star died without announcing itself to anyone. Picture the core collapsing straight down into a black hole. No explosion, no fireworks, no final act broadcasting itself across the universe. The star does not hide behind its own dust. It simply stops existing as a star. What replaces it produces no light. A black hole formed this way is invisible by its own nature, and no cloud of debris is needed to explain why no one saw it go. Hold that image next to what is supposed to happen. A normal massive star death, is loud in every sense that matters to a telescope. The core collapses, and that collapse triggers a shockwave, a wall of energy and pressure that slams outward through the star's remaining layers and blows them off into space. That is the explosion. That is the supernova. That is the event every observatory on Earth is built to catch, because it can outshine an entire galaxy for weeks. From the outside, a normal death looks like a sudden, unmistakable flare where nothing that bright existed the day before. A direct collapse looks like none of that. From the outside, there is no flare, no flash, no bright new point of light demanding attention. There is a star, and then there is not. The transition between those two states produces nothing dramatic enough for any camera to register. There is no quieting first, no gradual dimming, no countdown. As far as any distant observer is concerned, it simply goes from present to absent. Now picture what actually fails inside the star to make that happen. The shockwave that is supposed to punch through the outer layers and tear the whole structure apart. The wave every model expects to succeed stalls out partway through its climb. Instead of breaking free and ripping the star open, it loses momentum. The layers above stop being pushed outward. Gravity takes back control. The entire structure that should have been violently ejected starts falling inward instead, back down toward the core, back down into whatever is forming at the center. What should have been an explosion turns into a silent collapse, folding in on itself from every angle anyone could possibly be watching. And that is why this theory fits the data so cleanly. No explosion means no bright transient. No survey scanning that patch of sky, no matter how wide its coverage or how sensitive its detectors, would have caught anything to flag. The absence of any new point of light in the archives, the clue that looked so damning earlier in this investigation, stops being a mystery. It becomes exactly what you would expect. If confirmed, this would be one of the first times anyone has caught this kind of failure happening in something close to real time. A star going from clearly alive to clearly gone, with the years in between narrowed down almost to the decade. But we need to go deeper to understand how a star's death can fail this badly. We need to go inside the collapse itself and see what a death like this looks like when it works the way it is supposed to. Picture a massive star. For most of its life, it does one job: fusing lighter elements into heavier ones, releasing energy in the process, holding gravity at bay with the outward push of that energy. Hydrogen fuses into helium first. Once that runs out in the core, helium fuses into carbon, then carbon into neon, then onward through oxygen and silicon. Each stage burns hotter and faster than the one before it, and each stage builds a heavier element sitting at the center of the star like another ring in a tree trunk. That chain has to stop somewhere, and it stops at iron. Every fusion reaction up to this point releases energy, and that energy is what has been holding the star up against its own gravity the entire time. Iron breaks the pattern. Fusing iron into anything heavier does not release energy. It costs energy, pulling it out of the core instead of pumping it back in. So the star hits a wall it cannot fuse its way past. It builds an iron core, and that core just sits there, dead weight, producing nothing to fight gravity with. Gravity does not wait for a solution. Once the iron core grows past a critical mass, somewhere around 1.5 times the mass of our own sun packed into a ball smaller than most planets, the pressure holding it up simply fails. And when it fails fast. The core does not sink slowly. It collapses, falling in on itself at a meaningful fraction of the speed of light, a region the size of a small planet crushing down to the size of a city in a fraction of a second. That collapse does not go on forever. It hits a wall, and the wall is made of neutrons. As the core crushes down past the density of an atom, past the density of anything we can build or test on Earth, the particles inside get forced together so tightly that neutron pressure kicks in and refuses to compress any further. The collapse slams into that wall, and it rebounds. That rebound is the bounce, a shockwave born out of the sudden stop, and it starts racing back outward through the layers of the star still falling in above it. At the exact same moment, something else pours out of that crushed core. Neutrinos, nearly massless particles produced in staggering numbers as the collapse proceeds, carrying away the overwhelming majority of the entire event's energy. Most of those neutrinos just escape, passing through the rest of the star like it is not even there, because that is what neutrinos do. But not all of them. A fraction get absorbed just behind that stalled shockwave, dumping their energy directly into it, giving it a second wind right when it needs one most. If that reheating works, if enough of that neutrino energy lands in the right place at the right moment, the shock gets back its momentum. It punches outward through the rest of the star's layers, blasting the whole outer structure away from the core entirely. That is the explosion. That is a supernova bright enough to be picked out from across a galaxy, sometimes bright enough to briefly outshine every other star in its host galaxy combined. This is the textbook version. Iron core, collapse, bounce, neutrino reheating, shock breakout, supernova. It is the standard story, tested against decades of observed explosions, matched against a supernova close enough to actually confirm the neutrino burst directly. And it is the exact version this star, sitting in a small galaxy 75 million light-years away, appears to have skipped entirely. But the standard story does not always hold. Sometimes the shockwave never punches through. It stalls partway up through the star's collapsing layers, and it never recovers what it lost. The reason is a fight between two forces, and one of them is simply too strong. Material above the core keeps falling inward the whole time, piling on top of the stalled shock, adding weight and pressure from above at the exact moment the shock needs room to move. Neutrino heating is supposed to counter that, feeding energy back into the shock from below, giving it enough push to overcome everything stacking up on top. But that heating is not guaranteed to be enough. If the infalling material is too dense, too heavy, coming down too fast, the energy the shock gets back from those neutrinos cannot overpower it. The shock stops gaining ground and just holds still, caught between a push from underneath that is not strong enough and a wall of infalling matter that will not let up. Picture a wave rolling into a river mouth, trying to push its way upstream against a current far too strong for it. For a moment, it holds its shape, fighting forward, but the current does not tire and the wave does. It loses momentum first, then shape, then gets pulled under and swallowed by the very thing it was trying to push back against. That is what happens to a stalled shock. It does not explode outward in one dramatic failure. It simply loses the fight quietly and gets absorbed by the collapse it was supposed to stop. Once that shock fails to revive, the consequence is immediate and total. The outer envelope of the star, everything sitting above the core, was only ever going anywhere because that shock was supposed to blast it outward. Take the shock out of the equation, and there is nothing left pushing that material away from the star, so it does not go anywhere. It falls the same way it was falling before the bounce ever happened, except this time, there is no rebound waiting to catch it. Layer after layer, the envelope sinks back down toward the core instead of escaping into space. And that falling material does not just disappear once it reaches the core, it adds to it. Every bit of envelope that sinks back down piles more mass onto whatever sits at the center, and that center just keeps growing heavier as a result. Remember the wall that stopped the original collapse, neutron pressure, the one force strong enough to hold the crushed core together and keep it from compressing any further. That wall has a limit. Pile enough mass on top of a neutron core, and eventually even neutron pressure cannot hold the line anymore. There is no stronger wall waiting behind it. The core keeps gaining mass until there is nothing left to stop it, and it collapses straight through that final limit into a black hole. But here's the detail that matters most for everything we have been building toward. None of this produces a bright explosion. There is no shock breaking free, no violent transient lighting up the sky, no signal for any survey to catch. The entire process, from stalled shock to failed rebound to total collapse, happens without ever sending out the one signature every telescope is built to notice. It is not a quiet supernova, not a dim one. It is a collapse with no explosion at all, just mass falling inward until a black hole is all that is left, sitting in perfect silence where a star used to be.
So where is the line?
At what mass does a star stop being a normal supernova candidate and start being a candidate for this kind of silent failure? Astronomers do have a rough map for this, and it starts simple. Stars on the lower end of the massive star range, once they go through core collapse, tend to leave behind a neutron star. The core crushes down, hits that wall of neutron pressure, and stays there, stable, holding its shape against gravity. Push into higher mass territory, and the outcome shifts. Heavier stars become the candidates for black holes instead, because their cores start out bigger and keep gaining ground even after that neutron wall should have stopped them. Somewhere around 25 to 30 solar masses, the picture stops being clean. Below that range, models are fairly confident a star gets its explosion, but above it, the confidence drops off fast. This is the zone where simulations increasingly show either a weak explosion, one that barely manages to unbind the star's outer layers, or an outright failure, where the shock never revives at all and the whole structure collapses inward the way we just walked through. Cross that threshold, and you are no longer looking at a guaranteed supernova. You are looking at a coin flip, and the coin is not even weighted the same way from one star to the next. Part of what decides that coin flip is something researchers call core compactness. Think of it as a measure of how tightly packed the collapsing material actually is at the moment everything gives way. A loosely packed core has more room to work with, more space for a shock to gather strength as it moves outward. A tightly packed core is different. Everything is crushed closer together, denser, harder to push through, and a shock trying to fight its way out of that kind of structure runs into more resistance at every step. High compactness makes an explosion less likely, while low compactness makes one more likely. It is one of the better predictors astronomers have found for sorting stars into explodes and doesn't. And here is the part of the research that catches people off guard. This is not a simple story where heavier always means harder to blow apart. Some of the most massive stars in these models turn out to be easier to explode than stars sitting in the middle of the range. Because what matters is not just total mass, it is how that mass gets arranged inside the star as it evolves. Internal structure, the layering built up over millions of years of fusion, can make a moderately massive star's core surprisingly hard to blow apart, while a more massive star next to it, with a different burning history, ends up looser and more explosive. Mass alone does not decide the outcome. Structure does. This is exactly the kind of mapping researchers like Suchbold and Woosley have spent years refining, running detailed grids of stellar models through simulated collapses to chart which ones explode cleanly, which ones fail outright, and which ones sit in that uncomfortable middle ground. Their work is part of why astronomers no longer treat massive star death as a single predictable event. And this star, sitting at roughly 100 solar masses, is not hovering near the edge of that uncertain zone. It is planted well inside it, in the range where failure stops being a strange exception and starts being a real, live possibility. There is another factor in this star's story, and it has nothing to do with its mass. It has to do with what the star was made of, chemically, from the moment it formed. Astronomers call this metallicity, but the word means something different in this field than anywhere else. To an astronomer, a metal is any element heavier than hydrogen or helium. Carbon, oxygen, nitrogen, iron, all of them count. A star does not invent this material itself, at least not at first. It inherits it from the generations that came before. Stars that lived fused heavier elements in their cores, died, and scattered that material back into the gas clouds where the next generation forms. A galaxy full of older stars ends up rich in these heavier elements. A younger, less processed environment stays poor. That is metallicity, a chemical fingerprint of how much stellar history came before you. That fingerprint matters for how a star dies, and it comes down to wind. Stars do not sit still, burning quietly. They shed material constantly, driven outward by radiation pressure against their outer layers. Heavier elements catch that radiation far better than hydrogen and helium alone. More metal in a star's outer layers means a stronger wind, and a stronger wind means more mass gets stripped away and blown into space, year after year, for the star's entire life. A metal-rich star can lose a huge fraction of its original bulk this way, long before it ever reaches the moment of collapse. Flip that around, and you get the opposite outcome. A star with weak metal content has a weaker wind, plain and simple. Less material in its outer layers can catch starlight and get shoved outward, so it holds on. It keeps more of its original mass all the way through its life, right up to the moment its core finally gives out. Less stripping means more retained bulk, sitting there until collapse. Now connect that straight back to where this star lived. PHL 293b. the Kinman dwarf, is metal poor. That is not an incidental detail. It is exactly the kind of environment that produces stars, like the one at the center of this case. Stars that never got stripped down by strong winds. Stars that arrived at the end of their lives, still carrying an enormous fraction of what they started with. Carrying that much mass into collapse has consequences we have already walked through. More retained mass builds a bigger core, and a bigger core sits closer to that dangerous compactness researchers flag as the strongest predictor of failure. Tightly packed, hard to blow apart, resistant to exactly the kind of shock revival a normal supernova depends on. This is the profile that pushes a star towards silent collapse instead of a visible explosion. So look at what that means, standing back from it. This star was not just unusually massive, it was massive in an environment specifically built to let it stay that way. The galaxy itself, quiet and unremarkable as it looked from the outside, had already set the conditions for this kind of ending long before 2011, long before any spectrograph noticed a thing had changed. Everything that falls back does not vanish quietly the moment it hits the core. It adds to a process called fallback, and fallback decides how total this kind of death actually is. Once the shock stalls and gravity takes back control, the material above the core does not stop at some halfway point and settle into orbit. It keeps falling all the way down, sinking through whatever remains of the structure until it reaches the newly forming black hole and gets absorbed. There is no floor to catch it partway. No pressure left in the system strong enough to stop that fall before it reaches the center. Layer after layer, the star's own material becomes fuel for the very collapse that killed it. In the most extreme version, almost nothing gets left behind. The black hole consumes close to the entire mass of the star. Everything from the outer hydrogen layers down to material sitting just above the core when the shock first gave out. What gets ejected afterward is not a supernova's worth of debris. No scattered heavy elements. No glowing gas visible for months. It is closer to nothing. A death this complete barely leaves a signature behind at all. Picture the star's outer layers as a crowd packed into a stadium, all moving toward an exit the moment the signal comes to leave. That is what the shock revival should be, a door thrown open, everyone getting out. But in a failed collapse, that door does not open all the way. It seals halfway, and the crowd rushing toward it gets pulled back into the building instead, swallowed by what is forming behind them. Nobody escapes clean. Except not quite nobody. Even in the most total version of this failure, a tiny bit of material can still get out. The neutrinos, flooding outward the instant the core collapses, carry off a staggering amount of energy. That energy loss is not free. It comes directly out of the star's own gravitational hold on itself. Losing it that fast can loosen the grip on the most loosely bound material near the surface, just enough to let a small amount break free, instead of falling back down with everything else. That is the only chance any observer gets to see this event at all. And what it produces is not a flash. Not bright enough, not fast enough, not violent enough to register the way a supernova does. What little material escapes is faint, sometimes only detectable as a brief glow in infrared, heat rather than light, the kind of signal that requires the right instrument pointed at the right patch of sky at the right time. Hold on to that detail, because it becomes important later. That faint infrared afterglow is not just a footnote to this one star's story. It is precisely the kind of leftover signature astronomers have started hunting in other galaxies, looking for the same quiet fingerprint this star may have left behind. Prepare yourselves. We begin. Leave the Kinman dwarf for a moment, because another galaxy and another star offer a case file built to test everything we just walked through. NGC 6946, relatively close by, has produced supernova after supernova over the decades, so many that it earned the nickname the Fireworks Galaxy among those who track such events. You would expect that a galaxy known for going off regularly would show a massive star's death looking normal, but that is not what happened. This galaxy sits about 22 million light-years away, and when you set that next to the Kinman dwarf 75 million, you start to see why this case carries so much weight. Whatever is harder to catch at extreme distance becomes easier here. Instruments that can barely resolve a galaxy's integrated glow from 75 million light-years have a real shot at picking apart individual detail from 22 million. Here, the telescope actually has a fighting chance. The star itself was not an LBV, but a red supergiant, cooler and dimmer at the surface, yet still enormous, sitting somewhere around 22 to 25 solar masses. That number is no accident. It falls close to that uncertain boundary we spent the last several sections mapping out, the zone where models stop guaranteeing an explosion and start allowing for failure. A red supergiant at this mass is not as extreme as a 100 solar mass LBV, but it sits squarely inside the range where astronomers already expect some fraction of stars to skip the fireworks entirely. Then came 2009, and the star brightened not by a small amount, as over that year its output climbed by a factor of about 10, a jump large enough that anyone watching would pay attention. That brightening did not look like a supernova. There was no sudden spike, no violent surge slamming into peak brightness within hours or days the way a real explosion announces itself. What astronomers watched instead was a slow climb stretching over months, gradual enough that it read less like a detonation and more like a long building process still working its way towards something. And that is exactly how the astronomers watching it interpreted it at the time. A brightening like this, patient and sustained rather than instantaneous, fit the profile of a star in the early stages of something dramatic. The natural assumption was that this was the wind-up. A red supergiant swelling in brightness over months looked like a star doing exactly what massive stars do before their final act, building toward the shock breakout, the explosion, the moment every supernova survey is built to catch. The expectation was straightforward. Watch this star and eventually you would get fireworks, a slow climb now and then somewhere down the line, the payoff. Instead, they watched the opposite happen. What came after the brightening was not another climb, but a decline that did not let up. Month after month, the star's visible light dropped slowly at first, then steadily enough that anyone tracking its brightness could see the trend was not reversing, with no second wind, no plateau where it leveled off, no false bottom where it seemed to stabilize before shifting. It just kept fading in the same direction, year after year, like a light on a dimmer switch someone had turned and walked away from. By around 2015, that decline had run its full course, and the star was gone from optical view, not fainter, not hard to spot without a good telescope, but gone. In the sense that pointing every capable instrument at that exact location turned up nothing where a red supergiant had been sitting for as long as anyone had been watching that patch of the galaxy. Astronomers did not leave that as a vague impression. They put a number on it, because a claim this strange demands one. Whatever might still be sitting at that location, if anything at all, had to be putting out at most 1 or 2% of the star's original brightness. And that is the ceiling. Not a rough guess or an order of magnitude shrug, but a hard constraint built from how deep the imaging went and how far below the noise the star had dropped. Consider that number for a moment, because it is doing more work than it might seem. 1 or 2% is not a star that dimmed. Stars dim all the time for all kinds of ordinary reasons, and they are still there afterward, still detectable, still themselves, just quieter. This is different. A star that drops to 1 or 2% of its former output has, for all practical purposes, stopped existing in visible light. It has not dimmed. It has disappeared, using a word we have already had to reach for once in this investigation. That result did not come from a single glance through a single telescope either. Hubble and the Large Binocular Telescope both worked this case. The same careful way astronomers confirmed the Kinman dwarf's disappearance, comparing images taken years apart, matching them position by position, checking that exact coordinate against itself across time, rather than trusting a single snapshot. Hubble's archive stretched back well before the 2009 brightening, giving a clean baseline of what used to sit there, while the Large Binocular Telescope tracked the years after, watching the decline unfold and confirming image after image that nothing was creeping back into that spot. Two separate instruments, two separate datasets, landing on the same conclusion. The star that used to be there was not there anymore, and had not been for years. But a disappearance like this cannot get around one fact. A star does not just vanish and leave nothing in its place. Not if something violent happened, because mass and energy have to go somewhere. If this star failed the way the Kinman dwarf star may have failed, some residue of that failure should sit at those same coordinates, even if visible light cannot find it. So the search did not stop at optical. It moved into infrared, looking for exactly the kind of afterglow this investigation already flagged, as the one signal a silent collapse might actually leave behind. Optical light only tells you part of a story. It catches what is hot enough and bright enough to glow in the wavelengths our eyes can register, but it says nothing about heat that has cooled below that threshold or about dust, because dust does not shine on its own. Dust absorbs light from whatever is nearby and re-releases that energy as heat, and that heat shows up not in visible light, but in infrared. So if something survived that fade in a form our eyes could never catch, infrared was the only place left to look. Yet something was there. Long after the star had dropped out of every optical image after Hubble and the Large Binocular Telescope had confirmed there was nothing left to see in visible light, a faint source kept showing up in infrared observations at that exact location. Not bright, not dramatic. A weak, persistent glow sitting right where a red supergiant used to be, refusing to go fully dark the way the optical data had. Consider what produces a glow like that. When the star's structure failed, and its outer layers began the collapse we have already walked through, whatever material did manage to escape did not stay as bare gas forever. As it expanded and cooled, some of it condensed into dust, the same basic process that builds any dust cloud around any dying star. That dust then sat there, soaking up whatever radiation was still coming from the collapsing remnant underneath, and slowly re-releasing that energy as heat. Not a flash, not a burst, a quiet furnace running for years on borrowed light, exactly the kind of low-level signature a failed explosion was expected to leave behind. For a while that fit the story cleanly. A dying star, a weak ejection, a little dust, a fading infrared glow tracing all of it out. Then the newest piece of evidence arrived, and it did not fit as cleanly as the models had predicted. The James Webb Space Telescope pointed at that same location decades after the original 2009 brightening, and it found the glow was still there. It was still fading, still consistent with something lingering at that spot, rather than a clean, empty patch of sky. That part matched expectations, but what did not match was how bright that glow still was. If you run the simplest, failed supernova models forward to this point in time, they predict a certain level of infrared output, a dim leftover from a small, weak ejection of material. JWST measured something brighter than that, and not by a small margin either. The numbers researchers have put forward estimate the surviving infrared luminosity somewhere between 1/10 and 1/4 of the star's original output. That is a lot more residual light than a minimal, quiet collapse is expected to leave sitting around. That is not a detail you can quietly file away and move past. A brighter than expected glow does not just complicate the failed supernova story, it strains it. It suggests either more material escaped than the simplest models allow for, or something else entirely produced that dust and that heat. And that complication pushes a second theory into the picture, one that has nothing to do with a single star failing to explode at all. Some researchers looked at that same infrared excess and turned to a different explanation entirely. What if this was never one star failing to explode? What if it was two stars colliding and becoming one? A stellar merger is not some exotic edge case invented just for this problem. Binary stars are common, and when two of them spiral into each other, the collision itself can produce a burst of brightness that looks, from a distance, remarkably like the beginning of something explosive. That initial climb in 2009, the slow, months-long rise that astronomers first read as the wind-up to a supernova, fits a merger event just as well as it fits a dying red supergiant. Two stars crashing together throw off enormous amounts of material in the process. Material that behaves exactly the way the aftermath here behaved. It cools, it condenses into dust, and that dust sits around the wreckage for years, glowing quietly in infrared long after the visible fireworks have faded. A burst of light, a cloud of dust, a long fading afterglow. Every piece of that pattern matches what actually got observed. Merge two stars into one, and you would expect this exact sequence, brighten, fade, then glow faintly in infrared for decades afterward. But the merger idea runs into a wall the failed supernova theory does not have to deal with, and it is not a small wall. Remember the constraint Hubble and the Large Binocular Telescope placed on this case? The one capping any surviving object at 1 or 2% of the original star's brightness? That number was designed to test whether a star could still be sitting there, dimmed but alive. It functions fine against that question. It is a much harder fit for a merger, because a merger does not end with nothing left behind. Two stars combining often leaves a single more massive star in their place, and depending on how that remnant settled, it could put out more light than 1 or 2% of the original system. Forcing a merger remnant down to a brightness that faint requires its own set of assumptions. Ones, the data does not automatically hand you the way it does for a quiet collapse. So where does that leave the case? Not settled, and nobody studying it is pretending otherwise. N6946BH1 remains one of the leading real-world candidates for a failed supernova, the best example anyone has of a massive star collapsing directly into a black hole without the explosion everyone expects. But the merger idea has not been ruled out. It sits there as a live alternative, unresolved, pulling at the same infrared data that was expected to close this case and instead reopen the question. That leaves you holding two separate mysteries in two separate galaxies, a star in the Kinman dwarf gone without a trace, and a star in NGC 6946 faded to almost nothing, its true fate still argued over. Both cases open and still unresolved years after the data first raised the question. That starts to raise an uncomfortable point that is not about either star specifically. How often is this actually happening? Quietly, in galaxies nobody happened to be watching closely enough to notice. Step back from both cases for a moment, because together they point at something far larger than either star alone. Every telescope survey ever built shares one basic design assumption. It is watching for things that get brighter. A supernova works with that assumption perfectly, because it is, by definition, a sudden burst of light, where nothing that bright existed the night before. Build a wide-field camera, sweep it across the sky night after night, compare each new image against the last one, flag anything that jumps in brightness by enough to matter. That is the entire logic behind decades of transient astronomy, and it works. Thousands of exploding stars have been caught by exactly this method, automated pipelines doing the same comparison over and over, millions of times a night, looking for the one pixel that suddenly lit up where nothing lit up before. Think about what that pipeline is actually built to notice. A supernova gives it something to grab onto, a sharp, unmistakable spike, brightness climbing by orders of magnitude within hours or days, easy to separate from noise, easy to flag, easy to confirm with a follow-up look. The entire architecture, the alert systems, the software that scans millions of galaxies a night, the astronomers on call to check anything that trips the alarm, all of it is built around catching that spike. It is a smoke detector. It is tuned to notice fire, and it does that job well. But a smoke detector does not notice a room slowly going dark. And that same design has a blind spot built into its foundation, one you do not notice until a case like the Kinman dwarf forces you to confront it directly. A survey built to catch things getting brighter has no natural mechanism for catching things quietly getting dimmer. There is no alert built for a star that fades by a few percent a year, then a few percent more the year after that, sliding down gradually enough that no single comparison between two images ever looks alarming. A star that fades out over years instead of flaring up in a night does not trip any alert, not because the software failed, but because nobody wrote the software to look for that shape of change in the first place. Nothing about a slow decline looks urgent to a system tuned to flag sudden brightening. So, a star can spend a decade fading toward nothing, quietly, patiently, and unless someone happens to be pointing the right instrument at the right patch of sky at the right moment purely by coincidence, cross-referencing old data against new for some unrelated reason, that fade goes completely unrecorded. It just happens, and the sky keeps the secret. Consider how much has to align for a fading star to actually get caught. Somebody has to be looking at that exact patch of sky before the fade begins, then look again after, and think to compare the two on purpose. Nobody was doing that for the Kinman dwarf between 2011 and 2016. Nobody was doing that for N6946BH1 either, not in any systematic way, until an outburst in 2009 happened to catch someone's attention first. Take away that lucky outburst, and the red supergiant in NGC 6946 fades out of the record with nobody ever noticing it was gone. The only reason either of these two cases exists as a case at all is that somebody, for unrelated reasons, happened to be holding onto old data and thought to check it again. Now follow that gap to its logical end. If a star failing to explode looks like nothing to most instruments built to watch the sky, then the actual rate at which this happens could be very different from what anyone currently assumes. Every count of how massive stars die, how many end in visible supernovae, versus how many quietly collapse, depends on being able to see both outcomes equally well. We can see one of them easily. The supernova rate is measured constantly, cross-checked across dozens of surveys, refined year after year into a number astronomers trust. The other outcome, the quiet one, has no equivalent number because nothing was built to produce one. It might be slipping through entirely unnoticed, not because it is rare, but because nothing was built to catch it. That asymmetry matters more than it sounds like it should. Picture two bins astronomers are trying to fill. One labeled exploded, one labeled collapsed, silently. Every year, real events fall into both bins somewhere out in the universe. But only one bin has a net stretched under it to catch what falls. The other bin might be filling up just as fast or faster, and nobody would know, because there is nothing there to register the difference between empty and full. Every published estimate for how often massive stars end this way is really an estimate for one bin only, dressed up as if it described both. That is not a small problem sitting off to the side of this investigation. It cuts straight to the center of how astronomers think stars die. If failed supernovae are common, not rare exceptions, but a real fraction of what happens to massive stars every time one runs out of fuel, then decades of assumptions about how massive stars end their lives could be quietly wrong. Not because the physics was misunderstood. The physics of a stalled shock, a failed rebound, a core collapsing straight through into a black hole, all of that holds up fine on its own. The problem sits entirely on the observational side, because the tools were only ever pointed in one direction, built to notice fire, and never built to notice a room going dark. And the consequences of getting that number wrong reach further than just a tally of dead stars. Every estimate for how many stellar mass black holes should exist in a given galaxy depends on knowing what fraction of massive stars collapse quietly instead of exploding. Every model of how heavy elements get built and scattered back into a galaxy's gas depends on knowing how much of a star's processed material actually escapes in an explosion versus how much falls back into a black hole and never makes it out at all. A universe where quiet collapses are common is a universe that recycles less oxygen, less iron, less of the material that eventually builds planets, and eventually, everything standing on one. Get the rate of failed supernovae wrong, and you are not correcting one footnote. You are adjusting an input sitting underneath a whole chain of other conclusions. The obvious next question is whether anyone has actually built a tool pointed in the other direction. The answer is yes, in a specific and almost old-fashioned way. Instead of watching the sky in real time for something new appearing, you go back through the sky's own history. You take the oldest deep photographic surveys astronomers ever produced, sky maps stretching back decades, cataloging every star bright enough to register on a photographic plate. Then you hold that old map up against the modern sky, mapped in far greater detail by today's digital surveys, and you look for anything that was there before and simply is not there now. That is not a supernova search. It is the opposite of one, a search built entirely around absence, around finding the stars that used to be counted and have quietly stopped being countable. And there is a project doing exactly that. The project is called VASCO, and the name spells out exactly what it is built to do. Vanishing and appearing sources during a century of observations. Astronomers behind it took some of the oldest wide-field sky surveys ever produced photographic plates from the 1950s and built the entire search around a single, almost stubborn question. What does the sky look like now, compared to what a camera pointed at the same coordinates recorded 70 years ago? Picture what those original plates actually were. Glass-coated in a light-sensitive emulsion exposed for minutes at a time under an open shutter, then developed by hand in a darkroom. The same basic photographic process used for family portraits in that era, just aimed at the sky instead of a living room. Observatories ran these surveys for years, plate after plate, night after night, slowly building up a photographic record of practically the entire visible sky as it existed in the 1950s. Nobody digitized any of it at the time, because digital sensors did not exist yet. The record just sat in archives, drawer after drawer of glass plates, largely untouched for decades, waiting for someone to have a reason to go back and look at it again. That reason arrived once modern digital surveys caught up in coverage and resolution. Suddenly there was a second map of the same sky, taken with cameras thousands of times more sensitive, recording stars far fainter than anything the old plates could ever have picked up. And once you have two maps of the same sky, separated by 70 years, the obvious move is to lay one on top of the other and see what changed. That is the actual mechanics of the project, and it is more laborious than it sounds. Every plate first has to be scanned, turned into a digital image itself, because you cannot cross-match a piece of glass against a modern catalogue directly. Then every point of light on that scanned plate has to be assigned a precise position translated into the same coordinate system. Modern surveys use a process complicated by the fact that old plates were not calibrated to anywhere near the same standard as a modern telescope. Positions drift. Distortions creep in near the edges of a plate. Getting an old photographic dot to line up with a specific pixel in a modern digital catalogue takes careful, deliberate correction, not just placing two images side by side. Once that alignment is done, the actual search is a matching problem. Take a catalogue of hundreds of millions of points of light from the old plates, and for every single one, ask the same question. Does anything sit at these exact coordinates in the modern survey? If yes, move on, nothing to see. If no, that position gets flagged as a candidate disappearance and it goes onto a growing list. Run that question across the full footprint of these old surveys and the numbers start big, almost absurdly big. Tens of thousands of candidate disappearances come out of that first pass. Tens of thousands of points of light that the old plates recorded and the modern catalogues do not show. Look at that raw number on its own, and it sounds like the sky is bleeding stars by the hour. It is not, and the researchers running this project know it is not, which is why almost none of those tens of thousands survive any real scrutiny. Old photographic plates are noisy in ways modern digital sensors simply are not. Dust sitting on the glass at the moment of exposure, chemical flaws baked into the emulsion during development, scratches picked up over decades of handling and storage, processing artifacts from a darkroom technique that had no way to double-check its own output in real time. All of it can look exactly like a point of light where nothing ever existed. A speck of dust does not announce itself as dust. It just sits there on the plate looking like a star, indistinguishable from the real thing, until someone checks it against another plate taken on a different night. So the filtering starts there, at the most basic level. Does this candidate show up on more than one old plate, taken on different nights, or does it only appear once? A flaw baked into a single piece of glass only ever shows up on that one piece of glass. A real star, real object, shows up consistently across independent exposures. That first pass alone strips out a huge fraction of the initial list, candidates that were never anything more than a scratch or a speck of dust catching the light at the wrong moment. What survives that first cut still is not clean. Some candidates turn out to be cases of mistaken identity, an object misclassified the first time around or cross-matched incorrectly between one catalogue and another, because two separate stars happened to sit close enough together that an old, lower resolution plate blurred them into a single point, while the modern survey resolves them as two throwing the position off just enough to look like a disappearance instead of a measurement problem. Untangling that kind of error means going back to the raw images, both old and new, and checking by eye whether a genuine one-to-one match got missed by the automated matching software. And a large share of what is left after that turn out to be perfectly ordinary variable stars, the kind that dim below a survey's detection limit for a while, and then brighten again later. On a cycle, nobody happened to check twice. A star can sit bright enough to register on a 1950s plate, fade into obscurity for a stretch of years that has nothing to do with any modern survey's schedule, and simply not have been caught mid-brightening, the one time astronomers went looking. Ruling this out means finding independent brightness records for that same star, ideally spanning enough time to catch it in a bright phase somewhere in the intervening decades. Where that record exists, the candidate gets crossed off the list. Where it does not, the candidate stays open a little longer, neither confirmed nor dismissed. Filter all of that out. patiently, one candidate at a time, cross-checking plates against plates and catalogues against catalogues, and the tens of thousands collapsed down to something far smaller. A list that started in the tens of thousands narrows, after this kind of scrutiny, to a much shorter roster of objects that genuinely resist easy explanation. No dust speck, no scratch, no known variable star sitting at that position under a different name. And here is the honest state of that smaller list right now. Nothing on it has produced a confirmed case that actually demands new physics. No object Vasco has turned up, gives astronomers a clean, undeniable example of a star vanishing the way the Kinman dwarf star vanished, or the way N6946 BH1 faded into near nothing. Every candidate that has been run down so far has an explanation that fits inside physics we already understand, even if a handful remain technically unresolved, simply because nobody has yet tracked down the specific record needed to close them out. That might sound like the project came up empty. It did not. Even without a smoking gun case, Vasco does something just as valuable to this investigation. It puts a real number on how rare true disappearances actually are. Search tens of thousands of candidates across a century of sky coverage and end up with none that require anything exotic. And you have learned something concrete about the ceiling on how often this happens. These events are not common. They are not hiding in plain sight across every corner of the sky, waiting to be noticed. Which changes how you should look at the two cases this investigation has already spent so much time on. If genuine vanishing stars are this rare across a search this wide, then a star disappearing in the Kinman dwarf, and another fading to almost nothing in NGC 6946, stop looking like isolated curiosities. They start looking like exactly the kind of rare signal a project like Vasco is built to confirm exists at all. Vasco is not the only file in this cabinet. A handful of other objects belong in this investigation too, not because they solve anything on their own, but because they show this category of star behavior is bigger than two galaxies. Begin with VY Canis Majoris, a red hypergiant and one of the largest stars known, sitting close enough in our own galaxy that astronomers have tracked its behavior for a long time, and what they have tracked is dramatic. VY Canis Majoris does not hold a steady brightness. It swings, dropping by several magnitudes at a time, sometimes fading enough that a casual look would suggest something had gone badly wrong with it. Nothing has. The star throws off huge amounts of material in irregular bursts, arcs and clumps of gas and dust visible in images taken around it, and when a fresh batch of that ejected material sits between the star and us, it blocks a chunk of the light heading our way. The star's actual output barely changes. What changes is how much of that output makes it through the cloud it just built for itself. That distinction matters. VY Canis Majoris proves, through repeated observation, that a massive star can vanish from view in visible light without vanishing at all. The star is still burning, still fusing, still exactly as alive as it was before the dimming started. All that changed is the clarity of the path between it and any telescope watching. This is the survivor theory for the Kinman dwarf star laid out in miniature, happening in real time, close enough for astronomers to study the mechanism directly instead of inferring it from a distance. If dust can do this to a hypergiant we can watch directly, there is no reason it could not do something similar to an LBV 75 million light-years away, just at a scale we cannot resolve well enough to confirm. Then there is an older, messier category, historical nova records. Astronomers cataloging the sky for over a century have logged plenty of sudden brightenings they labeled novae at the time, using whatever photographic tools existed in that era. Go back and try to match some of those records against modern surveys, and a fraction of them simply do not have a source anymore. No object sits at the recorded coordinates. Some of these get explained eventually, reclassified as a different kind of variable or traced to a plate flaw from decades ago. Others do not, staying on the books as unresolved, an old detection with no modern counterpart, an origin nobody has recovered. Consider these cases together: a hypergiant that dims by hiding behind its own dust, century-old catalogue entries with no modern source to match them, two failed supernova candidates already walked through in detail. None of these are the same event, and none of them prove what happened to any other star on this list. What they build together is a pattern. Stars that disappear or dim past recognition are not some singular anomaly invented to explain one strange galaxy. They are a real documented category showing up again and again in different forms across different corners of astronomy. This is the context this investigation needs as we head back to the Kinman dwarf itself to weigh both suspects one more time with everything now on the table. Here is where it gets uncomfortable. Bring it all back to the Kinman dwarf, because that is where this case started and where it still lives, unresolved. The survivor theory says the star never died at all, that it threw off enormous amounts of material during that outburst. We know happened before 2011, built a shell of gas and dust thick enough to bury its own signature, and settled into a dimmer, cooler phase where the galaxy's integrated light just does not register it anymore. On its own, that was always a theory asking for a lot of trust. But now it is not asking alone. Vi Canis Majoris sits right next to it as proof. This is not some convenient invention. A hypergiant, watched directly, dimming by several magnitudes because of its own dust, still burning the whole time. If a star that close and that well-studied can vanish from view without dying, there is no reason a star 75 million light-years away, blurred into the light of an entire galaxy, could not do the exact same thing on a scale nobody can resolve. The failed supernova theory says something colder happened, the core gave out, the shock never revived, and the whole structure caved inward into a black hole without ever lighting up the sky. That theory does not need to borrow credibility from somewhere else either. Not anymore, because N6946BH1 already did the work. A star that brightened, faded past the point of detection, and left behind nothing but a weak infrared glow where a red supergiant used to be. If that happened once in a galaxy close enough to study directly, there is no reason to assume it cannot happen again somewhere farther out, somewhere harder to watch. Both of these comparisons do the same thing. They do not stretch physics to cover a gap in the data. They point at things already observed, close enough and clearly enough that nobody argues whether the mechanism is real. Dust can hide a star, and that is confirmed. A star can collapse without exploding, and that is also confirmed. Neither explanation for the Kinman dwarf star requires inventing something new. Both just ask you to accept that something already known to happen happened here too, in a slightly more extreme version than the precedent. And that is the frustrating part of standing here with two solid precedents in hand. They do not tell you which one happened to this specific star. Vi Canis Majoris proves dust obscuration is real, but it does not prove that is what happened in PHL 293b. N6946BH1 proves failed collapse is real, but it does not prove that is what happened here either. You can hold both theories up against real, documented, physically sound examples and still walk away with absolutely no way to choose between them. 2. Working explanations, both grounded in nature, both compatible with everything we have seen, and the case sits exactly where it did before either precedent got introduced. Precedent alone cannot break a tie like this. What you would need is something specific to this star, this collapse, this exact patch of sky, some signal that only one of these two scenarios could have produced and the other could not. And there is in principle a signal like that. The question is whether anyone could catch it from this far away. One signal travels out from every collapsing core, no exceptions. Whether the shock revives and the star explodes as a normal supernova, or the shock stalls and the entire structure falls silently into a black hole, the collapse itself unleashes an enormous burst of neutrinos in the first fraction of a second. Neutrinos are nearly massless particles that barely interact with anything at all, and in that instant they stream outward, carrying off the bulk of the energy released when the core crushes down to nuclear density. This is not a maybe. The physics of collapse demands it. Something that extreme happening to that much mass in that little time has to release energy somewhere, and neutrinos are where almost all of it goes. That sounds like exactly the kind of clean physical evidence this investigation has been missing. A signal tied directly to the moment of collapse present, whether the star exploded or failed, would settle a massive piece of this case immediately. Detect that burst, and you know for certain something collapsed at that location, at that moment, regardless of what happened to the light afterward. But here is where it gets uncomfortable. The Kinman dwarf sits 75 million light-years away. That distance alone makes neutrinos useless for this investigation. These particles are ferociously hard to catch even at close range. They pass through planets like ghosts passing through a room, unnoticed and unchanged. Building a detector sensitive enough to catch even a handful from a nearby event already takes enormous tanks of material buried deep underground, hidden specifically to filter out every other kind of interference. Stretch that same detection problem out to 75 million light-years, and the number of neutrinos actually reaching Earth from that collapse, spread across a sphere that size, drops to something no instrument humans have ever built could register. The burst happened, if it happened at all. It is simply gone, diluted across a distance. No current detector can overcome. Neutrino detection does work, but only within a much smaller range than this case requires. Events inside our own galaxy, or in the handful of neighboring galaxies close enough to count as our cosmic backyard, sit within reach of these instruments. That is the range where this kind of detection has actually succeeded before, catching a burst tied to a nearby collapse and confirming directly that a core gave out at a specific place and time. The tools built for exactly this job exist, and they work well. Enormous underground detectors, tanks of extremely pure material watched around the clock by sensors waiting for the rare flicker of light a neutrino leaves behind when it does finally interact. Some of them scan the sky in coordination, built specifically so that if a burst like this ever arrives, multiple detectors around the world can confirm it happened at the same instant. So the instrument is real, the instrument works, and none of that matters here. This is a case built around a galaxy, sitting at a distance that places it completely outside the range where any of these detectors could ever help. A perfectly good instrument, entirely useless for the one question this investigation actually needs answered. If neutrinos are off the table, the next question is obvious. What about gravitational waves? Space itself is not rigid, it stretches and compresses. And when something extreme enough happens to mass and motion, that stretching moves outward in waves the same way dropping a stone sends ripples across water. That is what a gravitational wave actually is. Not a beam of light, not a particle, but a distortion in the fabric of space, spreading outward from wherever it started, passing through everything in its path, including Earth. A collapsing core could produce exactly this kind of ripple, but only under specific conditions. If the material folding inward is spinning fast enough, or if the collapse happens unevenly, lopsided instead of perfectly smooth and symmetrical, that asymmetry shakes space around it. A perfectly even collapse, mass falling straight inward from every direction at once, barely disturbs anything beyond its own boundary. It is the wobble, the tilt, the imperfection in the fall that sends a signal outward. Whether the Kinman dwarf star's core collapsed with that kind of asymmetry is exactly the sort of detail nobody outside that galaxy could ever confirm just by watching light. A gravitational wave, if one went out, would not care whether the collapse was quiet or explosive on the outside. It would carry information from the very center of the event, untouched by dust, untouched by distance in the way light is, untouched by distance in principle, not in practice, not yet. Every gravitational wave detector currently running was built and tuned to catch a specific kind of source, mostly black holes and neutron stars colliding with each other, events that release a staggering amount of energy concentrated into a very short burst. Even those detections only work for sources within a few 100 million light-years, and only for the most violent collisions physics produces. A single star's core collapsing, even asymmetrically, does not come close to that scale of disturbance. Run the numbers on what today's detectors could actually pick up from something at 75 million light-years, and the signal a stellar collapse would generate sits well below what any instrument currently running could distinguish from background noise. This is not a permanent wall, according to the people building the next generation of these detectors. It is described openly as a goal, a capability planned for future instruments with far greater sensitivity than what exists right now. Machines designed specifically to reach down into fainter signals from farther away. That future tool might eventually catch a stellar collapse at this range. It does not exist yet, and pretending otherwise does not help this investigation move forward. So here is where the case actually sits. Neutrinos would answer this cleanly, if only the distance were not impossible. Gravitational waves would answer this cleanly too, if only the sensitivity existed yet. Both tools point at exactly the right question. Neither one can currently reach far enough to answer it. Every avenue that could break this tie with hard, direct evidence either fails because of distance or because the technology simply is not built yet. We stand in the gap between what physics predicts and what our instruments can see, which means the case sits exactly where it sat back in 2020 when ESO first published this. No new direct evidence, two suspects, both still standing, and nothing on hand capable of closing this file through observation alone. Set aside the Kinman dwarf for a moment and shift your attention to the detectors that catch black holes colliding. Since 2015, LIGO and Virgo have picked up dozens of these events. Two black holes spiraling inward, merging, sending a ripple across space that reaches Earth and records as a chirp in the data. Each detection includes a mass estimate for the two objects that merged. When astronomers lined up all those masses side by side, something did not add up. The black holes LIGO and Virgo keep finding are, on average, heavier than the ones astronomers have catalogued closer to home. Inside our own galaxy, the stellar mass black holes we have measured, mostly through their gravitational tug on a companion star, tend to sit in a lower range. The ones merging out in the deep universe, visible only to gravitational wave detectors, keep arriving larger, not by a small margin. The gap is wide enough that coincidence or small number statistics could not explain it away. That gap now has a name. Astronomers call it a mass gap, and it actually describes two separate patterns stacked on top of each other. There is a lower gap, a range of masses between the heaviest neutron stars and the lightest black holes, where almost nothing seems to exist, as if an invisible fence prevents objects from forming at that particular weight. And there is a separate, higher pattern, a cluster of black holes sitting in a heavier range than standard models predicted, appearing in merger after merger more frequently than earlier assumptions ever expected. Here is where it gets uncomfortable. For a while, that heavier cluster was a genuine puzzle. Standard supernova models, built around a star exploding, blowing off its outer layers, and leaving a comparatively modest remnant behind, do not naturally produce black holes that heavy in large numbers. An explosion, by its nature, throws mass away. The more violently a star blows itself apart, the less mass remains to collapse into whatever sits at the center afterward. Failed supernovae solve this cleanly. This is not a minor fix, it is nearly the entire answer. A star that never explodes retains almost all its mass, the outer layers falling back rather than being ejected. The core collapses, the envelope falls inward instead of blasting outward, and the black hole that forms ends up close to the star's full pre-collapse mass rather than a fraction of it. Run that process across a population of massive stars, and you get exactly the kind of heavy black holes LIGO and Virgo keep detecting. Formed quietly, no bright explosion required. Now return to the Kinman dwarf star, because it sits almost precisely within the conditions this mechanism requires. A metal-poor environment, weak stellar winds, a star that was never stripped down before collapse. An initial mass around 100 solar masses, already enormous before anything began to fail. Every ingredient the process asks for is present in that one small galaxy, 75 million light-years out, which means this is no longer a story about one star alone. If the collapse happened as the evidence suggests, it is not an isolated curiosity. It is one visible thread in a pattern that shows up over and over in the gravitational wave data, a pattern spanning galaxies no one has ever pointed a spectrograph at black holes forming in silence, leaving nothing behind but a slightly heavier signal decades later in a completely different kind of detector. Every scenario this investigation has weighed so far ends the same basic way. Either the star survives, dimmed and buried under its own dust, or it collapses into a black hole. Two outcomes, both leaving something behind, a star in one case, a black hole in the other. But there is a third ending in the physics of massive stars, and it is worth naming here because it draws a hard boundary around what this specific star could and could not have done. It is called pair instability, and it does not leave anything behind at all. Here is the mechanism, stripped down to what actually happens inside the core. In an extremely massive star late in its life, the core gets hot enough that the photons inside it begin carrying more energy than a basic physical limit allows for ordinary matter. Past that threshold, some of those photons stop acting as radiation pressure holding the core up and start converting directly into pairs of particles, an electron and its antimatter counterpart, a positron, popping into existence out of pure energy. That conversion is the whole problem. Radiation pressure has been holding the core up against gravity this entire time. The moment a chunk of that pressure gets converted into particle pairs instead, the core loses support it was depending on, and it starts collapsing faster than it should. That collapse is not gentle. It is not quiet. The sudden inward fall spikes the temperature even further, hot enough to ignite oxygen fusion explosively, all at once, throughout a huge portion of the core, rather than in the steady, layered burning a star normally relies on. That kind of runaway ignition does not produce a controlled response. It unleashes an explosion violent enough to tear the entire star apart, not just blow off the outer envelope the way a normal supernova does, but unbind the whole structure, core included. Nothing is left afterward. No neutron star, no black hole, only an expanding cloud of debris where a star used to be. Here is where it gets stranger. This mechanism does not apply to every massive star, and it is not the mechanism this investigation has been chasing for the Kinman dwarf case. Pair instability only becomes relevant at a much higher mass than the star this investigation has been tracking. It takes a helium core somewhere in the range of tens of solar masses before the process even starts, and full disruption, the kind that leaves nothing behind at all, needs a core even heavier than that. The Kinman dwarf star's estimated mass sits below that ceiling, high enough to be a serious candidate for collapse, not high enough to enter the range in which a star simply detonates itself out of existence. That distinction carries real weight. It proves stars can disappear through more than one channel, that vanishing is not a single uniform kind of event with one explanation always waiting behind it. And it draws a clean line under this particular star's fate. Whatever happened, happened in the collapse or hide range, not the get obliterated entirely range. Full disruption was never on the table here, which returns the investigation to the two suspects that have stood throughout, and to the question of what, if anything, could finally settle which one actually happened. The team behind the 2020 paper did not simply close their laptops and move on. They had a plan, return to the same patch of sky, this time with Hubble, and take another pass. Do not expect a clear photograph of the star itself. At 75 million light-years, even a star as extreme as this one cannot be resolved as a single point by any instrument. Its light blends into the galaxy's overall glow. What Hubble could offer was precision, sharper spectral measurements, tighter brightness, limits a more refined version of the same integrated light. This entire case has depended on from the start, squeezed a little harder for detail than the VLT data had managed. Consider what each outcome would actually mean. A positive result would not look dramatic, no bright new dot appearing where the star used to sit. Instead, it would be a faint residual signal in the spectrum, consistent with a dimmed, dust-buried survivor still contributing a small amount to the galaxy's total glow. Not proof the star is back, but proof something remains, exactly the shape of evidence the survivor theory needs to move from plausible to likely. A negative result would mean continued absence, no signal, no trace, nothing beyond what the rest of the galaxy would produce on its own. That would not prove a collapse, but it would tighten the noose around the survivor theory, making it harder to argue that something is hiding when even a more sensitive look keeps finding nothing. So where did that follow-up actually land? As of the most recent published information, there is no widely reported Hubble result that overturns anything. No headline confirming a lingering star. No headline confirming its final absence either. The two-scenario picture that ESO published in 2020 is still standing exactly as it was, unmoved by whatever Hubble did or did not find in the years since. That is not a satisfying place to leave a follow-up plan sitting, and it is worth being honest about it, instead of dressing it up as more conclusive than it is. Hubble, for now, is not the tool that will break this case open. If an answer is coming, it will not come from an instrument already in the sky. If Hubble is not the tool that breaks this case open, something else has to be, and there is already a name attached to it. The extremely large telescope, built by the same organization that first caught this star's disappearance, is under construction right now with a mirror far bigger than anything currently pointed at the sky. Bigger mirrors gather more light and resolve detail that smaller instruments physically cannot separate out. That is the entire point of building it, not to replace Hubble or the VLT, but to see past the limit those instruments keep running into every time this case comes up. That limit is the key to understanding why this case is so difficult. Every observation made so far, going back to 2001, has looked at this galaxy as a single blurred source of light. Not a star, not a cluster, a smear, all of it mixed together, because nothing built before now has had the resolving power to pick individual bright points apart at 75 million light-years. The ELT is designed specifically to push past that. Point it at PHL 293b, and it could, in principle, start separating out individual bright sources or tight clusters that are currently sitting on top of each other in every image ever taken. That capability lands directly on top of the two theories this whole investigation has been carrying. If the star survived, dimmed and wrapped in its own dust, the ELT might isolate a faint point of light exactly where the LBV used to sit, too weak for anything built before now to pull out of the surrounding glow. If instead the star truly collapsed, and nothing but a black hole sits at that location, now the ELT should find nothing at all, no faint survivor, no hidden star, just an empty patch of light exactly where something used to be. Either result would be a real answer, not another hedge. This is the first instrument that could actually test the difference between a star hiding and a star gone, instead of gathering more indirect evidence to argue over. None of that is available yet. The ELT is not finished. Current projections put first light sometime in the late 2020s, which means this case genuinely cannot be closed. Not because nobody is trying, not because the physics is too complicated to model, simply because the one instrument built to answer this specific question has not turned on yet. So if you're watching this expecting a clean resolution, here is the honest version instead. This mystery has an expiration date already stamped on it, a real one, tied to a real telescope with a real construction timeline. That date just has not arrived. In the next few years, someone will point a mirror at this galaxy and get an answer nobody currently has. Until then, the case stays exactly where it has been sitting since 2020, and it is worth pausing here before the next telescope changes anything, to sit with what that kind of unresolved waiting actually says about how much we really know. Before this investigation goes further, understand, this was never building toward a solved case. Every chapter so far has circled the same edge, the point where the data runs out and the explaining stops. That edge is the actual subject, not the star, not the black hole, the edge itself. Consider what that means. A clean final answer would be easier to accept. You would hear it, file it away, move on. Instead, this case hands you a shrug from the people best equipped to give you something more. That is a different kind of unsettling, and it deserves to be named directly, not dressed up. But here is where it gets uncomfortable. The standard teaching of stellar death in classrooms and textbooks and documentaries like this one treats it as settled ground. Massive star runs out of fuel.
Core collapses.
Shock revives. Supernova lights the sky. A remnant remains. Clean stages. Clean logic. No asterisks. This case is the asterisk. A star with every property that should have guaranteed a spectacular death simply stopped being there. And nobody can tell you with certainty which of two endings actually happened. That is not a footnote to settled physics. That is a crack running straight through it. And this does not come from the fringes of the field. Not an amateur stargazer flagging a blip in a personal dataset. The astronomers who publish this run the very large telescope. They work through the European Southern Observatory. They put their names on a peer-reviewed paper in a major journal, and then told the world plainly that they do not know which of two explanations is correct. Professionals with the best instruments on the planet looked directly at this problem and walked away without a firm answer. That is not a failure of effort. It is an honest report of where the evidence stops. And recall what came up a few chapters ago, the blind spot built into almost every sky survey ever designed. Instruments built to catch things flaring up, with no way to flag something quietly fading into nothing. If that blind spot is real, and there is good reason to believe it is, then this case is no rare outlier. It might be one visible example of something happening far more often than anyone has been able to count, hiding behind the same gap in coverage. This is where the investigation has been heading all along, underneath every chapter, not toward an answer for one star in one small galaxy, toward a much bigger, much less comfortable question. How many other stars have already gone the same way? Unnoticed, unrecorded, sitting in that blind spot nobody built a tool to see into. Ask the question straight out. What if quiet collapses are not rare at all? What if the assumption underneath a century of astronomy that massive stars announce their deaths with light has been wrong in a way no one has had tools to catch? The night sky may have already lost stars, plural, more than we know, more than the 2 cases we have investigated. Every one of them could have slipped past because nobody watched that exact patch at that exact moment. That question carries weight. A huge amount of what astronomers claim to know depends on getting it right. Every estimate for black hole numbers and typical masses starts from an assumption about what fraction of massive stars explode versus collapse in silence. The models of chemical enrichment, how elements like oxygen and iron get built and scattered, depend on knowing how often that scattering happens. Fewer explosions mean less material gets out, galaxies enrich slower, and every prediction for gravitational wave detection rates traces to the same number: how many stars fail quietly instead of loudly. Get that number wrong, and you're not just wrong about one star in one dwarf galaxy. You are wrong about a foundational input feeding half a dozen other fields. This is exactly the gap the next major survey is built to close. The Vera Rubin Observatory, running its legacy survey of space and time, is not designed the way older surveys were. It is not built mainly to catch things flaring up. It is built wide, built deep, and built to repeat. It scans huge sections of the sky over and over on a cadence no previous project has managed. That repetition is the whole point. A survey that only looks once catches explosions. A survey that looks again and again patiently, across years, catches the opposite. It catches a star that was there last month, and is not there now, at a scale where that absence gets logged instead of missed. Give that kind of monitoring a few years to run. What comes out the other end is not another single case study to argue over. It is a number, a real statistical count of how many massive stars quietly vanish across a measured sample compared against how many go out in a supernova. That is the piece missing from every argument made so far. Not another precedent, an actual rate. This puts one small galaxy, and one star that stopped being there between 2011 and 2016, in a strange position.
It was never about just this star.
It is one visible thread in a pattern astronomers are only now building tools to measure. Depending on what that measurement finds, this case might become one of the first data points in a reckoning that is still entirely ahead of us. So close the file the way it actually sits, not the way a tidier story would want it to sit. 75 million light-years out, in a small metal-poor galaxy of no particular distinction, there sat a star,
roughly 100 times the mass of our Sun, burning at something near 2.
5 million times the sun's brightness. It dominated its surroundings without trying. Astronomers tracked it for over a decade, watching its spectrum return the same way year after year, the unmistakable fingerprint of a massive star in its final unstable phase. Then, sometime between 2011 and 2016, that fingerprint simply stopped showing up. Astronomers found no flash, no alert, no bright new point of light in any archive they checked. Nothing but a star that was there, confirmed, documented, repeated across 10 years of data, and then wasn't. 2 suspects have run through this investigation from the start, and neither one has been ruled out. The first holds that the star is still out there, wrapped inside the wreckage of its own outburst, dimmed past the threshold where any instrument can pull its light free from the galaxy's glow. That theory requires nothing exotic, just an ordinary process. Dust obscuring a source, pushed to an extreme version of something already seen happening elsewhere. The second says the core gave out. The shock that should have blown the star apart never revived, and the whole structure collapsed into a black hole without ever lighting up the sky. That theory needs nothing exotic either, just a known failure mode, the kind current simulations already predict for stars at this mass in this kind of metal-poor environment. Both explanations fit everything observed. Both are grounded in mechanisms astronomers have watched happen in other stars, under other circumstances, and neither one holds any advantage over the other. Not because nobody has looked hard enough, but because the tools that could separate them, a neutrino burst, a gravitational wave signal, sit beyond what is possible at this distance. Not broken tools, absent ones, or tools not yet sensitive enough to reach this far. The instruments that might eventually break this open exist mostly as blueprints and construction timelines right now. Mirrors still being ground, detectors still being designed, sensitivity still being built toward a threshold nobody has crossed yet. Which leaves the tension exactly where it has sat since 2020. Somewhere in that galaxy, right now, one of two things is true. Either a star sits behind a wall of its own discarded material, still burning, still alive, invisible only because of what it threw off before going quiet. Or a black hole occupies that same coordinate, formed without a sound, without a flash, without a single photon announcing that anything had happened at all. Both possibilities occupy the same patch of sky. Only one of them is real. That patch of sky is still there, and nobody has stopped watching it. Every so often, a telescope somewhere gets pointed back at that same small galaxy, checking again, just in case this time something is different. The next real lead in this file is not a theory. It is a machine, a mirror bigger than anything currently built, scheduled to open its eye on the sky before this decade ends. That mirror might resolve exactly what sits where that star used to be, or it might not. Nobody gets to promise an answer just because the hardware finally exists. If you want to be here when that answer comes, or when the next case like this opens up elsewhere in the sky, this is where that kind of investigation keeps happening. Stay close for the next one. For now, sit with this. The light reaching Earth from that galaxy tonight left its source 75 million years ago, long before anything resembling a human stood anywhere on this planet. That light carries the last confirmed trace of a star that dominated its galaxy's glow for who knows how long before anyone here noticed it existed at all. And somewhere in the gap between when that light left and when it arrived, the star it came from may have already stopped being a star in more ways than the data has figured out how to say yet.